So we know that we have several ways to divide the domain. Okay, one way considers that all cells will have the same size, delta x and delta y. Okay, delta x in horizontal and delta y in vertical direction. While another approach considers that for cells at extremity, we need to consider nodes on the boundaries. So if you want to take nodes on the boundaries, then for these cells, okay, they will have a different size. And you will have for any cell at a corner, the size will be delta x over 2 in horizontal and delta y over 2 in vertical. If I take a cell, for example, the following one, okay, in this direction, it is normal, it will have delta x, but in the perpendicular direction, the size will be delta y over 2 because the node here is at the extremity of the domain, okay? And if you take now a cell, if you take a node on the vertical face, okay? So for example, cell 0.7, you will have delta x over 2 for this size, and delta y for this cell here. So delta y and delta x over 2. So depending on the position of the cell, you can determine what are the dimensions, okay? And for a corner, you will have delta x over 2 and delta y over 2. Now, once we select the method to divide the domain, okay, next step will be to consider what are our nodes, and we need to name them. And you can consider, for example, since you have 3 millimeters in this direction, okay, you can say that I need first at the extremities, I need points on the extremities, okay? And since I have delta y over 2 and delta y over 2, so if I want to put my points, this is point 1. I can consider that in vertical direction, the size of this first cell is delta y over 2, so it's 0.5 millimeters. Now, for other cells in the domain, okay, I will have a normal size. So I have here, if I take the node here, okay, this distance will be 1 millimeter. And then, so here it's not a node, okay, let me just, okay, so here it's not a node, okay, let me just fix it. Here it's not a node, okay, you have a second node here. So this is 1 millimeter. And finally, you have now the cell, and until now you have 0.5 plus 2, 2.5. So for the final cell, the node will be at the corner here. Okay, and this distance is 0.5 millimeter. Okay, so in total, you will need 4 nodes on this boundary because the size is 3 millimeter. Okay, you always have, whenever you select this type of grid, the number of nodes will be on a certain face, okay, will be equal to the length of this face, which is 3, over the size delta y, which is 1, plus 1. And you need to add 1 because you have the, as we know, for the corner cells, the size is over 2. Okay, that's why you will have an additional node. While if you consider the other approach, and if I tell you use a grid in which all cells will have same delta x, same delta y, you will divide in this way. You have, this is 3 millimeters. You just divide it into equal parts. Okay, and then your nodes will be at the center of cells. You will not have any node on the face. This is the difference. Okay, while here you consider that nodes will start from face. So we have in this approach, we'll have the cells will be divided in a different way. So if I put on the same figure with another color to see the difference, then you will have the division in this way. Okay, and then the nodes will be the following ones. This is the first node. This is the second. This is the third. And this is the final one. Okay, so in this method, you will always have an additional node on the face because you have delta y over 2 and delta y over 2 from this side. Okay, now, in order, once we do this, next step will be to determine the total number of nodes that we have. We said we have here 3 millimeters. In this direction, we have 5 millimeters. So we need on this face 6 nodes. So you can divide into 1, 2, 3, 4, 5, and 6. And the distance between nodes will be 1 millimeter. Okay. Now, since you have here 2 millimeters, then if you divide into 2, you have 2 millimeters and delta y is 1. So you have delta y and delta y. And if you want to put your points, you will just take points on corners. And you will have an additional point here. Okay, so you start from the corner and then you move delta y until reaching the other end. So here, as expected, the number of nodes will be the length, which is 2, over delta y, which is 1, plus 1, since we are considering points at corners. So the total number of points in this way will be 3. Okay. Now you can put numbers to your points in order to facilitate the solution after. So here we have 1, 2, 3, 4, 5, 6. Then we can count 7, 8, 9, 10, 11, 12 for the second row. For the third row, we have 13 to 18. And for the final row, since we have only here 2 millimeters, so we'll have 3 nodes. 1, 2, 3. So it's 19, 20, 21. Okay, so once we do this, now we are ready to write the equations for each cell. So we should identify, if you want, what are the cells that are similar to each other, because we can write the equation once and then we can deduce for other cells what will be the relation. So first, let us identify what are the cells that are similar. Okay, so to start with, again, let us see the domain. Okay, if we look at our boundary conditions, we can, for example, if we look corner, okay, this cell is subjected to which type of boundary conditions? You have an adiabatic condition from this side, which is the same for node 6. Okay, so for cell 6 also, you have here adiabatic condition. You have from this side, you have convective condition with the outer fluid. And here also, you have a convective condition from this side with the outer fluid. While for these two other faces, so if you take these two faces are within the solid domain, so use the type of heat transfer through these faces is conduction. So you have conduction at this level and conduction at this level. Similarly for node 6, okay, for cell 6, also you have conduction from these two faces. So we have similar conditions for these two. That's why the equation will be very similar, okay? So let us write the equation first for cell 1, and then from here we can deduce the equation for cell 6. So if I start with cell 1, okay, I just need to apply the condition. I put my fluxes. So as we said, we have adiabatic condition here. So here we can say that for the adiabatic condition, Q second is equal to 0. Now, for the convective side, if we assume, let's say that the convection flux is coming inside, so if you put it in this way, then the expression of Q second here will be equal to H out times T infinity out minus the temperature of the node, so minus T1. Okay. Now, if we consider conduction fluxes, so we have two conduction fluxes, as we said, one coming from cell 2. Okay. So we need to write conduction between nodes 2 and one from cell 7. So we can say that Q second conduction that is coming from 2 to 1 is equal to K times. Since we assume that it's coming from 2 to 1, so we take T2 minus T1. Over the distance between points 1 and 2, which is equal to delta x. So over delta x. Now, if you want, since we might not have same area everywhere, let us find the rates. Yani we multiply Q second by A. So first here, for the convective flux, we need to multiply by area 1, which is this area here. Okay. To find this area, you need to know the size. So we said that this size is delta x over 2. And if we consider that we have a unit depth, so we can multiply the convective flux to have the rate. We multiply here by just delta x over 2. Now for the conduction is also taking place at this face, and this face is characterized by an area of delta y over 2 times 1. So we need to multiply here by the area 2. So we need to multiply by delta y over 2. Now, if you have a uniform grid size, if they tell you you have a uniform grid size, so delta x equal delta y, then you can simplify these two terms. The same for conduction that is coming from cell 7. So if we want to take A3, which is the area of the face through which we have this conduction, times the Q second from 7 to 1, so we can write it as K times T7 minus T1 over the distance between nodes 7 and 1, which is delta y. And we multiply by the area, as we said, we multiply by area of face 3. So this is our face 3 here. This is our face 3. The length of this face is, the area of this face is delta x over 2 times 1. So we just have to multiply here by delta x over 2. And if we have uniform grid, similarly, we can simplify these terms. Okay? So now, once we evaluated all flux, all heat rates through this cell, we can write the equation. So we can write that sum of E dot n equals to 0 terms. We get that, so if you divide all your terms by K over 2, you will get as equation T2 plus T7 minus 2 times minus 2 plus H0 delta X over KT1 equals to minus H0 delta X over KT infinity. Okay, so this is our source term. This is the coefficient A1. Okay, and this is the coefficient of T2, A2, and this is for T7, A3. Okay, so we were able to determine the coefficients for the different temperatures for cell 1. If we want to deduce from this energy equation, what will be the equation for cell 6? We say 6.6 is equivalent to what? 0.6 is equivalent to 0.1. Okay, while if I consider 0.7, 0.7 for cell 1 is equivalent to 0.12 for cell 6. So I can say that I need to replace 7 by 12. Okay, and if I consider the equivalent of node 2 is node 5. So if I have 2 for cell 1, it's equivalent to node 5 for cell 6. So now I can deduce that the equation for cell 6 will be, I replace T2 by T5. So T5 plus T12 instead of 7, 12. Minus 2 plus H0 delta X over K. Instead of T1, I put T6. And for the convective term, it will remain as it is because both are subjected to H characterized by H0 and T infinity 0. Okay. And in this way, we are done with equations of cells 1 and 6. Okay. Now, if we look at node 2, we can see that the conditions on nodes 2, 3, 4, and 5 are the same because all of these will be characterized by a boundary of convection with the outer environment. And we have here two sides of conduction with an area of delta y over 2 times 1. Okay. And we have one side of conduction with an area of delta x times 1. So let us write the equation for cell 3, for node 3 or node 2 if you want. You can write the equation for any of these nodes and deduce the equation for all others. Let us do the equation for node 2 and we'll deduce for 3, 4, and 5. Okay, so if I consider the equation for node 2, first, what is the convection flux? So it's plus H times the area. The area is the area of this face, which is delta x times 1. So H out times delta x times T infinity out minus T2. Now I have conduction from all other sides, okay? So if I take this face between 1 and 2, the area is delta y over 2 times 1. So I do plus k times delta y over 2 times, so now since between 1 and 2, it's T1 minus T2. And the distance between the two nodes is delta x. So over delta x. Okay. Plus, now for the conduction coming from 3 to 2, so it's plus k delta y over 2 times T3 minus T2 over also delta X. And now for the value of the flux coming from cell 9, from cell, sorry, 8, okay? So the area of the face here is delta X times 1, and the distance between nodes 2 and 8 is delta Y. So it's a plus K times delta X times T8 minus T2 over delta Y equals to 0. Okay, now I can do several simplifications. As we said, delta Y equals to delta X. I can simplify. And if I divide all terms by K over 2, okay, I end up with the following. So I have T2. So for the coefficient of T2, let us see what we have. We have first minus H0 delta X, and if I divide by K over 2, I will get 2 H0 delta X over K. So I can say that the coefficient of T2 will be minus 2 H0 times delta X over K. And I also have T2. I have T2 here, so it's minus 1 and minus 1 because I simplified K over 2, so minus 2. So minus 2. This is the coefficient of T2. While for points, for nodes, if you want 1 and 3, okay, the coefficient is just 1. So I have plus T1 plus T3, okay? While if I consider for 8, okay, it's plus 2 T8 because here I just have K, not K over 2. So when I divide by K over 2, I get 2, okay? So I will rewrite the equation here. So the coefficients will be the following. I will have T1, okay, plus T3 plus 2T8 minus 2 times H0 delta X over K plus 2T2 equals to minus 2H0 delta X over K T infinity 0. Once I know the form of equation, I can deduce for all nodes. يعني هن I did it for node 3. I did it for node 2. I obtained exactly same if you want form. But I have equivalent points. يعني if I consider 2, 2 is equivalent now to 3. When I take cell 3, it's equivalent to 3. When I consider cell 4, point 2 is equivalent to node 4. And when I consider the equation of node 5, 2 is equivalent to 5. Okay? Now, for cell 2, point 8 is the one just below it. Yani when I consider cell 2, point 8 will figure out. But in cell 3, instead of 8, I will have the point just below 3, which is 9. And I will have 9. And in cell 4, I will have 10. And in cell 5, I will have 11. Now, when I considered node 2, I have to take the point before and the point after. So I had here point 1, okay, which is equivalent in cell 3 to node 2, in cell 4 to node 3, and in cell 5 to node 4, etc. Okay, and finally, here I considered the point just after, which is a 3. So 3 will be equivalent to 4 for node 3, to 5 for node 4, and to 6 for node 5. Okay, so now if you want, I can deduce the equation for all other cells. Okay, and now I can say, let us write what will be the equation, for example, for cell 4. Okay, so here, instead of T1, I say 1 is equivalent to what for cell 4? It's equivalent to 0.3. So I should start by T3. So T3 plus. Now, when I considered cell 2, it's plus T3. 0.3 is equivalent to 0.5 when I consider the equation of cell 4. Okay, so I should put plus T5. Now, 0.8 is equivalent to 0.10. So when I write the equation of cell 4, I need to consider the conduction from lower side. I need to consider 0.10, يعني plus 2 T10